presentation that I'm going to give is quite broad in scope, and aspects of it aren't my area. I have pulled them together just to provide quite an overview of what the situation is in New Zealand, and I think what we need to be considering. So I'll have a little look at municipal wastewater in New Zealand and the types of discharges that we have here. And then we need to think about how we make decisions and look at a holistic approach, and there are a number of other considerations as well. It's not just where we want to put our discharge. This is not the problem, I guess, of district councils. This is our wastewater and the responsibility of all of us, and we need to, as a community, all become involved in the decisions around what we want to do with our waste and how we manage it. And I'll touch a little bit on biosolids as well. Okay. When we look at municipal wastewater in New Zealand, we have 330 wastewater treatment plants. 18 of them are large and 312 of them are small. When we look at the large plants, you'll see these are treating populations of greater than 35,000 people. So Rotorua is one, Palmerston North. Most of the discharges, you can see, are actually going to water. Less than 10% going to land, and some of them are going to a combination of water and land. When we look at the small treatment plants serving populations of less than 35,000, the majority of the discharges are still going to water, but you can see that there are more land treatment systems associated with smaller communities. And I just acknowledge Lowe Environmental for this overview of the New Zealand situation here. When we look specifically at the discharges to water, most of the discharges are going to the sea, and around 20% of the discharges are going to rivers. When we look at the discharges to land, you can see that around half of them are high rate applications, and the other half are to a mixture of either grazed areas or trees or cut and carry systems. And I think it's interesting when we look at the whole situation to note that of the 15 large plants, wastewater treatment plants that we have in our country, only 3 are discharging to land, and that's likely to be because of practical reasons. We have Taupo, Whangarei and Rotorua, and I'm going to talk a little bit more about Taupo and Rotorua. Okay. Where these outfalls and discharges are, you can see offshore ocean outfalls. There are many of them. Of course, we're an island country, so that's not unexpected. We have some shoreline marine outfalls, a few major river outfalls, and some major land treatment systems. So most of the water in New Zealand is being discharged to the marine environment through outfalls of one type or another. This is an interesting slide here. Just when you're looking at ocean outfalls, you can see that HDPE pipes are used, and these are very flexible pipes. They absorb wave motion, outstanding resistance, and very transportable. I mean, these ones here have been can be towed for 3 weeks through the ocean to wherever it is that they need to go. And they can be installed through a number of mechanisms here: dig and lay, or float and sink. it's a big thing, ocean outfalls in New Zealand, and there are different things, we're well served by them, there are different things happening internationally, and those global trends are still relevant, and we do have International Water Association specialist outfall groups that are a good vehicle for keeping up to date with knowledge and experience in that area. These same HDPE pipes are what we're using now in our reticulation systems as well. So not only are they very resilient in the water, they're very resilient to areas that are prone to earthquake movement and as well. Yeah. Shoreline marine water discharges. So the discharge isn't as far out to sea, it's a bit closer to shore. There's some international interest in what we're doing here in New Zealand, and specifically with the projects like we have in Hastings, where solutions have been developed in conjunction with tangata whenua and considered how you can put nature to work and do biotransformations in the treatment plant. So we end up with no sludge options. No sludge perhaps isn't quite the correct term, but no paru options, no human waste, because there is a biotransformation that is taking place. And then following that process, there is a discharge to the marine environment. The freshwater discharges that we have, a few examples here: Hamilton, Palmerston North, Huntly, Te Awamutu. The discharges from the treatment plant can either flow to or be piped to the waterways. They can enter the waterways via things like gabion walls, through ponds, discharge ponds, or piped directly with diffusers at the end of the diffusers. You can also use multi-port diffuser design, so when the discharge goes into the surface water, it can go in various places and allow for the mixing that needs to be taking place for compliance with the consent conditions. And the sensitivity of the receiving environment is going to, and the expectations of the community are going to drive what sort of level of treatment you need prior to your discharge. Discharge via wetlands. It can be engineered or constructed wetlands or floating wetlands. They're becoming a little bit more common now. And when we're discharging to a wetland, I guess it's important to remember, as one of the other speakers has already said, that the volume of water that goes into the wetland, unless you're in Australia, is also going to come out of the wetland. You know, the water is going somewhere, no matter where you put it. Whether it's actually on land, it's going to pass through the land and end up in surface waters, whether it goes through wetland. So it's being returned to the environment, and we just need to make some decisions around where we want it to be returned to. Constructed wetlands can usually improve the quality of the treated wastewater that has been discharged, but it can be variable and has seasonal influences as well as is influenced by rainwater. And as well, and one of the other speakers mentioned as well that you can actually treat the water to a very high standard and then pass it through a wetland, and it will come out with more pathogens and E. coli at the other end. So we need to think really carefully about where the weather and where wetlands are appropriate. When we look at discharge to land, remember half of the discharges to land in New Zealand are through high rate irrigation. These are through things like, passing through wetlands or through rapid infiltration beds. So instead of taking up a whole lot of land to put the water through, you use a smaller area of land, so there's a smaller footprint, and you just pour the water through. It can soak through or pass through constructed beds or even natural beds, like I think in Tarawera Scoria is a really good soil for infiltration beds. These sorry. In this one here, there's been a close working relationship here in the Cambridge wetlands and the rapid infiltration bed combination here between Tangata Whenua and Council, and they were in a bit of a dilemma really, because what was happening was the infiltration beds with so much water passing through can create tomos and scour out any road, so they can be problematic and it's difficult to overcome those issues, and what the current proposal there is that the treatment plant will be upgraded and UV added to the process, and then a direct river discharge. So we have instances here in New Zealand where people are actually moving away from rapid infiltration beds because of the issues that we're having with them. As I mentioned, the small land area is the big advantage. They can be effective, but only if the soils and the groundwater and other factors are suitable, and it's something that we've really looked at quite closely in Rotorua, and actually couldn't find anywhere that was suitable for a rapid infiltration bed. Other speakers have talked about this, managed aquifer recharge. There are trials in Canterbury and there's growing interest in it, but it's not something that's common in New Zealand yet. What we do have these discharges to land that are slow rate irrigation. They require large land areas, and in one of the examples that Rob presented, Robert, before, he had a population of, I think, 10,000 was his example, and that required 300 hectares of land. I'm not sure what your population is here, but I'd suggest that that's one of the main constraints against slow and contribute to crop growth, but very important to understand the sites and to make sure that there is sufficient land to irrigate. We have some good news, I guess, and some bad news examples in New Zealand. Taupo cut and carry system is definitely a good example. They have, you can see the land that's irrigated here with pivot irrigation. Relatively flat land. That's View Road. There are two schemes there, View Road and the older Rakanui, where they had pop-up sprinklers. Pop-up sprinklers were fraught with issues. Pivot irrigation seems to be working very well, and with that type of irrigation it's very easy to actually crop that grass and take the nutrients off. This system is very efficient at removing nitrogen, and the phosphorus is stored in the soil. The cut and carry provides revenue, and a significant amount of revenue that can significantly offset the costs of the operation. And the other advantage is it requires relatively low tech. Well, you're using relatively low tech wastewater treatment prior to irrigation. When we look at the View Road site in Taupo, it's currently irrigating 380 kilograms of hectare of nitrogen a year, and it's leaching in different years less than 20 or less than 30 kilograms of nitrogen per hectare, so incredibly efficient nitrogen removal. The consent allows them to apply up to 550 kilograms a year, but trials indicate that if they were to irrigate and apply that load of nitrogen, that they would likely breach the consent. At the Rakanui site, it's had a higher application rate, and there's it appears that phosphorus might be increasing in the groundwater now. The other site that I know is the one that we have in Rotorua, and it's slow rate irrigation. The treatment plant here is designed to treat for a population of 70,000, and we have on average 19,000 metres cubed a day that is treated and then applied to the land treatment system, which is here in Waka Forest. Close proximity to the treatment plant, only 3.3 kilometres from the plant, and only 120 metres higher than the plant, so looks ideally situated. Oops, sorry. The soils there have an incredibly high instantaneous infiltration rate. You can just pour the water on and it will go through. So we don't see overland flow from that site. So in 1991 we ended up with an easement there on 360 hectares of land, and at that point in time it was Crown Forest. And we've been discharging 70 millimetres a week. You can see it's via the sprinklers here that are about 1.2 metres high. And the benefits of this system is that the land need not be flat. Unlike Taupo, where you need to get a machine in to try and cut the grass and take it away, we don't need any machines on here. So this rolling hill country here, well, it's quite steep in places. We've found that as well here, these soils have very high phosphorus retention, and we've been operating the system now for 26 years, and we're only now just starting to see phosphorus move through the system, so this phosphorus loss is starting. We've been applying on average, I think, around 100 kilograms of phosphorus a hectare a year, so it's a huge load of phosphorus. That has been incredibly beneficial for the water quality of Lake Rotorua as well, because for 26 years that phosphorus hasn't gone to the lake. So it's probably the single biggest factor and action that's happened so far in Rotorua to date to improve the water quality or to prevent further deterioration in the lake. We rely on the land for pathogen reduction. We're not disinfecting at the wastewater treatment plant. We're removing down to around 5,000 E. coli, so the level's pretty high. And the constraints here really are, as I mentioned, it's a large land area that's required, and we have only 350 hectares, but we're only irrigating about 200 hectares of that. By the time you remove the area that's in roads and the pump station and the ponds and all the buffer areas, it's not all available, and we're actually irrigating down into the toe of the slope and the low levels in there as well. So a large area of land doesn't mean that you can actually irrigate the whole area. But the biggest problem, of course, with this site is the radiata, the trees, commercial forestry operation, and the uptake of nitrogen is minimal, unlike grass. So because the plants aren't taking up the nitrogen, we have had to, over the years, upgrade our wastewater treatment plant significantly to remove nitrogen at the treatment plant and not rely on the land to remove the nitrogen. The other constraint, it's incredibly high cost to operate this, even though it's only 3.5 kilometres away and 120 metres up. We're pumping 20 million litres of water up there to the ponds and then out to the blocks every day. The cost is about $1.2 million operational cost a year. And we don't get the revenue because we don't own the crop and we don't own the land. The other main constraint in the area now is that public are excluded from this area because the E. coli levels in our discharge are very high, which is not a very easy thing to do, because I don't know if you know Whakarewarewa Forest now. It's full of mountain bikers and mountain biking tracks, and they just keep popping up all over the place. And great place for mountain biking, but a bit of a problem trying to irrigate in areas where people are trying to ride mountain bikes. Looking a little bit more closely at nutrient removal, this black line here, this is the mass of nitrogen that we've been applying to land over time. This is 1991 through to now. And as I mentioned, our treatment plant has got more efficient at removing nitrogen over time. So you can see that the nitrogen that we discharge has reduced over time. And it has been incredibly variable, more variable than it needs to be. I guess because we had the land treatment system, it meant we could sort of play around with the treatment plant a little bit, and we've tried different things there. We took sort of some yeast waste and dunder and tried that as a carbon source, and ended up being a bit of a disaster for the plant. But and what we see, this is what we apply to the forest, and this is what leaves the forest, the green line, the nitrogen. So over the first few years, really from up until about 2002, it looked absolutely fantastic. A huge reduction in the amount of nitrogen in the water that was leaving the forest. But as you can see over time, there's less and less nitrogen removed. And really what had happened in this period of time for the first 10 years is that nitrogen was just stored in the ecosystem in general, but predominantly in that soil and in that soil water. And then it became saturated with nitrogen, and now we're in a bit of an equilibrium phase where we do have some nitrogen removal. It's predominantly through the natural wetlands there, and a bit of crop uptake and some volatilisation. So you look at it and think, well, is that a benefit now, that amount of nitrogen that's being removed? Not so sure for the cost that we spend. But when you look at phosphorus removal, it's just phenomenal. This is 30 tonnes a year that we have applied to that site. And it's basically all been held in the soil. This is the total phosphorus that we measure. We measure the phosphorus and we measure what leaves the site in a stream that drains the site. It's basically a single catchment, and we have a permanent monitoring station, and we just collect water samples from the stream once a week. Flow proportional, it's actually collected for the whole period of time during the week, and we just go and take the sample once a week for testing. This is total phosphorus leaving the site, and it looks like it's up and down, and it's well below, below generally our consent limit. And all of these peaks and things, they're related not to our irrigation system, and they're not really related to the amount of phosphorus that we put on the site. They're related to sort of erosion events, mostly that occur through the forest, and it's mostly particulate phosphorus. But what I don't have is the graph that shows the dissolved phosphorus that is starting to move through the system, and that is phosphorus that we have applied. It's not phosphorus that's coming from the soil. If we look at the effect on the stream of our discharge to land, these are the concentrations in our discharge, 2.2 milligrams a litre of phosphorus. Very low levels, of course, in the stream before we started irrigating at that site, and we have increased the level in the stream, so that we do see phosphorus moving through that system. But Nitrate, of course, that's mobile through the soil, and we are well and truly in equilibrium and have saturated that site now with nitrate. And what's important for our lake is the mass. It's the total load of nutrients that go to that lake in any year. So we were applying let's see. Before we started our land treatment system, we were discharging 150 tonnes of nitrogen to the lake. Our wastewater treatment plant, the process was, well, not good relative to today's standards, to say the least. 150 tonnes of nitrogen. The design of the land treatment system was to discharge 60 tonnes of nitrogen. Some of it would be taken up by the crop. Not very much, you can see, nothing like a grass crop or some of the other crops that you'll be using, irrigating. It was thought that there'd be quite a lot of denitrification in the upland soils and through the natural wetlands that were there. And the expectation was that 24 tonnes of nitrogen a year would leave. And what we've found, interestingly, if you look at the average over the whole period of time, which was in those first 10 years basically, the nitrogen didn't move, and in recent years the nitrogen has been moving through the system, but on average we have applied 61 tonnes of nitrogen to that site and have lost on average 28 tonnes of nitrogen a year to the lake. Recently, this is what we're doing now. We're only applying 40 because we've spent so much money upgrading our treatment plant, and we have around 23 tonnes moving to the lake. What we're looking at now is an alternative to the land treatment system, and upgrading our wastewater treatment plant so that we will achieve 26 to 30 tonnes leaving our wastewater treatment plant and not rely on the land. So a number of people have asked, well, what about other things that are going on in the catchment or in your area? If we look at the lake, because the lake is where everything, all of the nutrients that leach from our catchment, they end up in the lake before they go down the Kaituna to the sea. And the nitrogen, after we've treated our human waste, from our wastewater, is only 5% of the total load of nitrogen that's going to the lake. So as a community, and of course led by the Regional Council, we're all looking at now, well, we know we have determined how much nitrogen and phosphorus our lake can handle. We call it the sustainable load to the lake, and it's 435 tonnes of nitrogen a year. And our treatment plant's discharging 30. We're currently, in our whole catchment, discharging, well, based on the land use at the moment in the catchment, we would have a load of about 760 tonnes of nitrogen going to the lake. So it's a huge problem. So we have this program at the moment to try and reduce the pollution and the nitrogen by 320 tonnes a year. It's amazing. So that 435 tonnes, that's our sustainable load. We're in the process of sort of sharing that out, and it's not pretty. Everybody wants it. It's expensive. It's expensive to try and remove these nutrients from the water. Of course, as a district council, we feel like we have spent a lot of money upgrading our wastewater treatment plant, and we've gone from our 150 tonnes down to 30 tonnes. We're now expecting the farmers, the rural sector, to do their part now. We had thought in the 1980s, when we planned our land treatment system, that would solve all of our lakes' problems. And what we didn't realise at that time was the lag between what's happening on the land and the time it has taken for that nitrogen to reach the lake. So intensification of land has meant that over time we've had increasing loads of nitrogen going to the lake. So it's a difficult situation. We have just been working with the Regional Council because we have an allocation system already proposed for the 435 tonnes. I don't think anybody's happy with it. We were allocated, I guess by default, our 30-tonne consent limit, which we felt was going to constrain our growth. How were we going to grow our city if we had a mass limit that was fixed? And then we sort of thought, well, as our city grows, it's going to grow into what is currently farmland. And the farmland has an allocation as well. So if you stop farming and you turn it into urban land, well, there was an allocation for that farmland, so it doesn't just disappear. So we've looked at accounting for the transfer of nutrients from that rural land to the urban land as we grow. Some of it will be just normal land losses, and a portion of it will end up by going to the wastewater treatment plant, because as we subdivide and develop and put in sewage reticulation pipelines, we take that sewage to the treatment plant and discharge it. So we're going to allow for that in our treatment plant discharge. So every new house that we reticulate onto what is currently farmland, we're going to transfer 1.4 kilos of nitrogen and add it to our mass discharge limit. So that's, we've been working on that probably for the past year, and we're in agreement on that, which is actually really good. So while we do have a mass limit, we are able to transfer those nutrients basically from the rural sector as houses are, as it's subdivided, to our treatment plant discharge. Our consent is due to expire in 2021. It was state forest, Crown land, when we registered the easement on the land, which gave us the right to discharge in perpetuity. That land has been returned to the rightful owners, to the owners of the land, through a Waitangi tribunal settlement, treaty settlement. The owners of the land don't want the land treatment system there anymore. Well, a lot of the public don't want it there anymore either, because they'd rather mountain bike in it, and actually the land was returned to the owners. The right for the public access, to allow private public access, remains, and our easement actually does remain on the land as well. But can we continue to impose a discharge to land when the landowners object? It's difficult situation. The easement, even though the easement allows us to continue to irrigate, the easement was subject to a management plan on that site, and that management plan allowed for irrigation as well as growing a commercial forestry crop. Because we have only been irrigating 200 hectares of land, because we only had a little more than 200 hectares of land available to irrigate, you know, the example that we used before, it really wasn't enough. We need 500 or 600 hectares of land to irrigate in a sustainable way. And we have had an impact on that site. We have, it hasn't been metals. We've looked at the metals, and the metals that we've applied over time, and we've measured what's in the soil. Absolutely no problem at all with metals. We're not going to breach any metal standards for probably 100 years. But it's too much water, and when we put on 10 millimetres a day, you know, 70 millimetres a week on average, of course when we have all these huge rainfalls we're putting on a whole lot more, that soil is essentially saturated all the time, especially in the lower parts of that, the lower lying areas. The whole groundwater table's risen, and we have increased areas of wetland, but that because the soil is saturated for most of the year, the trees, they're just not getting enough oxygen. And we had Douglas fir trees there and radiata trees, and we've essentially killed Douglas fir. And the radiata, we have affected the health of the radiata significantly to the point where the forestry owners could, under our agreement, claim compensation. Apart from the upland areas, about 25% of the site is sort of higher up and quite steep slopes, and the water drains from that area really quickly, and also we're not irrigating as much on that area either, because it's very difficult to maintain the pressure, equivalent pressure in that whole block. So if the pressure drops, the top areas get irrigated a bit less. So we have seen a 25% increase in productivity in those trees in the higher parts of the irrigation area, and basically death of the trees in the lower lying areas. So a real mixed bag, and for the treatment plant we can pretty much achieve our consent conditions. But the other issue that we've only just recently had is our treatment plant. We were, up until 2017, our peak flow had been something like 42,000 cubic metres a day, so a little over double our normal daily flow. But with this increased rainfall event, we ended up by having 60,000 and then 72,000, but I think was the last one, 72,000. We never dreamed we were going to see flows like this coming through our plant. The flows for 24 hours exceeded the volume that our final effluent pumps could pump to the forest. So while we overflowed at the end of our treatment plant for 24 hours. It was at the end of the treatment plant, which was quite good, but well, better than at the beginning of the treatment plant. But you know, we don't disinfect, we don't remove phosphorus, so that was a huge load of nutrients to the environment, and given the way our climate's going, we sort of foresee more of that. So we also need to upgrade our treatment plant to deal with this capacity and with peak flows, and of course to do a whole lot of other work in our network to deal with our peak flows. So we need a major upgrade of our treatment plant, and we're looking at the benefits of the land treatment system. So it's not just about the discharge. We need to think about the inputs into the wastewater treatment plant, the amount of energy that's used, the chemicals that are used, the labour and the cost, and the remainder of the water will go to an ocean outfall. So combination of factors, and you know, that will give you quite a bit of sort of flexibility around where you want to put the water. And it's not just the discharge as well. They're looking at the sustainable approaches to the inputs, and somebody asked about the inputs into the system, and what can we do, and you know, should we get rid of those garbage things in our kitchen? I can't remember what they're called. Yeah, incinerators, that's right. And I guess there are a number of other things that we can do as well. We found that in our homes, a lot of the load of phosphorus that comes to the treatment plant, or almost, you know, a third to a half of it, is coming from our dishwashing powders. So stop using dishwashing powders with phosphorus in it, and then we won't have so much to remove at the treatment plant. And these artificial sweeteners and these things that we all have a responsibility, I guess, to try and do what we can, and it's well, we I guess as a treatment plant, and we operators don't want to end up by being sort of the ambulance at the bottom of the hill. So yeah, the whole community needs to come together to work on solutions. So sustainable approaches to the inputs. And another question that somebody asked was about the amount of water that comes in. For our treatment plant, it does have an impact on the amount of nitrogen that leaves, because every cubic metre of nitrogen that leaves or has, well, you know, we know that what leaves our plant is around 5 milligrams a litre, so every litre has 5 milligrams of nitrogen in it. So if we put more water in at the beginning of our plant, even if it's clean water, it's still going to leave with 5 milligrams a litre of nitrogen in it. So on a day where we double the flow through the plant, we double the nitrogen that comes out the other end. So we do need to control the water that's going into our plant, not just to prevent overflows, and not just to make the performance as good as it can be, to actually just stop the nitrogen leaving. So we're seriously looking at what flows we take into our treatment plant as well. And after our last few weeks, we'll be putting a whole lot more money back into looking at inflow and infiltration issues. Operating that streamlined is something that we really should be aiming for. The more complicated we make it, the more likely there are for things to go wrong. And I guess don't take this quite the wrong way. Streamlined, we need to be including the technology that we can monitor and control it, but not add too many different bits and pieces that detract from the main purpose of the plant. So we've upgraded our treatment plant a couple of times, well, a number of times now, and you get to the point where parts of it are really old, and you might look at it and think, you know, really we want to spend $40 million on our upgrade, but that's too much money. We really only have $30 million if we push it in our budget. So the pressure's on to try and spend less money. And what we do when we put that much pressure on, I mean, you can only cut the cost so far, and then you're actually making bad decisions, I think, around how you spend the money. And we're in a situation where we could take all of our inflow through one part of our plant, and the flow through the plant will be easy to manage. But because there's a pressure on the capital expenditure for our upgrade, we're considering taking some of the water this way and taking some of the water this way, and it's going to be very difficult to operate, and we're not going to get the best performance out of it because we're not actually putting the dollars in that we need to put into it. So, and we have had a quantitative microbial risk assessment done on our proposed upgrade. I think I'll just skip over this as well. What it has shown us is our proposal is to go to full membrane treatment. It's sufficient to make the water safe enough to swim in, safe enough for recreational use, theoretically, if we wanted to do that. But if we wanted to make it suitable for unrestricted use, as in the guidelines that Kevin discussed, we